Now Professor Chris King got canceled.
I recorded right between when I said that when you said that, but now it's permanent. It's out there forever.
Wait, so me saying it?
Yeah,
Oh,
no,
dang.
no one cares. Myself.
That's true.
All right, so where are we in this class? I'm getting you an exam study guide today so that you have a sense of the topics. None of these should be horribly surprising, but obviously feel free to send me an email, come swing by office hours next week and talk about any concerns you have about what's on that document. We should be covering just about the rest of it today. If you submit an assignment by Monday, I guarantee it's turned around. And the later you submit, the less likely it is that it's going to be turned around to you by the time the exam happens. But given that this is a little smaller class than it's been historically, I don't foresee there being too many issues with getting it turned around. It's really just if no one turns it in on Monday, if everyone turns it in on Wednesday between 11 and midnight, then the TA has a very short window to get that back to you. So as long as some people are submitting throughout next week, it's likely that everyone will get feedback in a reasonable amount of time. So if you have that ability to submit early, your assignment's in a pretty good state. You don't think you're going to do too much work on it, go ahead and submit that early. It'll make the flow a bit better for everybody. All right, anybody have any questions before we dive into that last bit of content that is likely to show up in some capacity on the exam? All right, last time we were in the middle of regular expressions and talking about how to form those, what those mean, how they relate to recursion, how those relate to mathematical expressions. And we got a couple of practice problems with regards to just thinking about converting regular expressions into set notation and looking at what elements are in those sets, as well as converting them into English and being able to describe in a nice, brief, coherent way what a language represents that is represented in a regular expression. We're going to get to the meat of it now, where we want to be able to write regular expressions for actual language definitions. So the first one is going to be the language of all strings in binary, where that string has at least one pair of consecutive zeros. So how would you define a regular expression? Recall that we can use star closure, we can use concatenation, we can use set union, and we can use parentheses to override that order of operations. And I gave you from the highest order of operation to the lowest order of operation. We will do star closure first, or you can also use positive closure if you want to as a shorthand.
If that was in the star closure, doesn't that imply that it includes the empty string, but then we wouldn't accept the empty strings because we choose zeros?
Yeah, so the such that gives you a conditional on that, so doesn't really give you any information about, it's in the star closure, so yeah, we're discussing, we start with the entirety of, yeah, the star closure of the language, such that says that we're going to reduce that domain down to anything that was in that star closure that also has, so you can kind of see it like an and. Logical and. Where the first half of the and doesn't reduce the domain at all. True and something. We have some solutions?
Yes.
All right. How do people think about the problem?
I was thinking about the leading, anything before and after the pair of zeros.
Yeah.
I generated, all the binaries, 0 + 1 star closure.
Yeah, so that's an excellent piece to note here, is that we can utilize this concept of what comes before and after what we care about is arbitrary. How do we syntactically represent this concept of arbitrary? And so that's going to be any number of anything. So you can utilize this concept of just 0 or 1 repeated an arbitrary number of times. And this just says anything. It's the equivalent of the English anything. What comes after that? Our pair of zeros right next to each other. What comes after the two zeros? Anything, because the two zeros don't have to end the number. There's nothing that specifies where these two zeros are. So you just repeat this concept of 0 or 1 star. And note that the 0 or 1 star can also include pairs of zeros. This just says that somewhere there is a pair of zeros. And what comes before and after it does not matter. The star closure can also go away because it is 0 or more. So this accepts the string 0, 0, because this star would say this happens 0 times. This happens 0 times. Here's the guaranteed 0, 0 that happens in the string. It would accept 10,000 zeros. There would just be lots of ways to potentially construct that string with this regular expression. Where is this pair of zeros? Is it the first pair of zeros where this is nothing and this is every 0 that comes after that? You would have lots of abilities to move, have this pair of zeros be any pair of consecutive zeros in that number. When we're parsing this, what we're likely to do is map this to the first pair of zeros that we find. That'll be more computationally efficient.
That would be the greedy approach for a pattern matcher, right?
Yeah.
Yeah.
Yep. Questions on that? Yeah, we can represent an arbitrary string denoted by 0 or 1 star. So we can just say 0 or 1 star, 2 zeros, 0 or 1 star. Some more of them. No pair of consecutive zeros. We're gonna make it a little bit harder. So exactly the same definition, but now we want to ensure that anywhere in the string, we will accept any string until we see that pair of zeros. As soon as we see that pair of zeros, garbage, not in the language. This one is much harder. I say it's much harder, but it probably isn't much harder if you have a good moment of insight. That's usually how these kinds of problems work.
Having experience with regular expression,
Like
or
that.
building regular expressions.
Yeah,
Right. 'cause then
Yeah.
you start.
So I can kind of get myself out of that space.
I like the.
Yeah.
Star closure on that second.
Yeah, that's good.
what I have.
Well, I kept working under all these other cases.
People have an answer? Anyone want some additional time to work and continue to think?
I agree.
The moment of insight comes from thinking that whenever a zero happens or occurs, it has to be followed by a one. So what kinds of partial strings can we build such that when we see a zero, it is immediately followed by a one? That also allows for an unlimited number of ones to come in a row. As soon as you do something like, you can get into the, all right, so pairs of characters, let's think about 0, 0, 0, 1, 1, 0, and 1, 1. If you think about that line of thinking, there's no way to guarantee that your 1, 0 isn't followed by a 0, 1, creating that pair of zeros in between the pieces that you're thinking. How do we get around that? You concatenate it with a 1. If we see a 1, 0, then we need to see a 1. It turns out that we don't need to think of this in terms of pairs of characters necessarily. We only need to think about it in terms of pairs of characters if the first character is a 0. So you might think something like substring may be preceded and followed by an arbitrary number of 1s when we do see that. So here is an incomplete answer, but my question for you is, why doesn't this work?
Because it doesn't allow for multiple zeros after 0, 1.
Yeah, this is forcing the string to end with a 1.
Oh,
Yeah.
Well,
I was gonna say it also doesn't allow the string to start with a 0. Or never mind.
Yeah, if this 1 star goes away, we can start with a 0, but yeah, this is just saying that every 0 is followed. So if you find yourself in this headspace, you might generate something like this and know that there's kind of 2-dimensional repetition. In this, we have a star closure of individual characters, and then we have a star closure of an idea. This is kind of like building objects from objects. Same kind of constructive idea. But yeah, this forces the string to end with a 1, which is not good. Anything that consists of all 1s, this forces there to be a 0 in the string.
this, oh, that's true.
So I'm going to give you a very long-winded answer that you might generate by thinking about it logically and then creating it from scratch. And here we go. So you might want to, if you started with this idea and said, okay, that's great, but we also want it to be able to end with a 0. So here is how we allow it to end with a 0. We can say either a 0 comes or nothing comes at the end of this. You can union this with all strings that generate a bunch of 1s with still that optional 0 at the end, because otherwise we haven't handled that. So this is what I'm going to call a hacked together answer that starts with a good idea and then really tries to make that idea work. We see this in programming all the time. You have some assumption about how the problem works, and there is a solution out there that consists of that component, but it balloons your answer to be large and difficult to read, even though it technically works. Is there a simpler answer? Did anyone come up with a simpler answer? Yeah.
In parentheses, 0, 1. After the end parentheses, there's a star union parentheses 1, 0, and that parentheses is also star plus 1 star.
So this. Okay, so we have the ability to repeat an arbitrary number of either 0 ones or 1 zeros. But you have to do them in that associated order.
Doesn't the union mean it can go in either way?
Yeah, so you would have either this or that.
Or the 1 star.
So yeah, there should be a plus as well. So union, union, and then is there a star outside of this that allows you to repeat these ideas? Because this is saying all the 0 ones come before. Or yeah, you do this, union that. But how do we repeat something like if there's a 0 1 and then a 1 0 and then a 0 1? So we would need something like allowing for repetition of this whole idea.
Then you can do 1 0 0.
Yep, because now as soon as we have that 0 1 and that 1 0, you start by selecting this, and then you repeat and can select this. I think there is an even simpler answer. Anyone have a sense of?
I'll take a shot.
Yeah.
Okay, so my solution was 1 star on the left. Then in parentheses, 0 followed by 1. With the plus closure on the 1.
Positive closure?
Yeah, and then close parentheses, star closure, that parenthesis group. And then in parentheses, 0 or empty string. That was what I arrived at.
Okay. That's good. That's pretty good. In fact, this is very close to what I think the final shortest answer will be. I think that this is a brilliant recognition here that the only way to generate substrings are consisting of either 1 or 0 1. But then we don't allow the string to end with a 0, so we need to reuse this 0 or lambda that allows for an optional 0 at the end. So I think we can shorten this even a little bit to basically 1 or 0 1, star closure that, and then allow for the 0 or lambda at the end. This allows you to repeatedly pick either a 1 or a 0 1, because the 0, if we see it, must be followed by a 1. And then we know that whenever we finish this, the last character that was done was a 1, so we can append a 0 to the end safely. And that allows for all strings that end in 0.
So anything plus lambda is like the question mark in
Yeah.
regular expressions.
Yeah, the optional
Yeah.
Boolean. Yeah. How do we feel about that? Does that make sense? Does it seem simpler than this answer that was hacked together based on this idea? I think that even analyzing something like this can help you to see how sometimes re-engineering your solution or trying to simplify the assumptions that you make can lead to significantly cleaner code. I just see there being a correlation there, or something to learn in that domain from this kind of exercise. Questions on this construction? I think that's what I have as answer number 2 here. Yeah. So this to me is the simplest and most readable answer. But again, it's a regular expression. As long as you are correct with it, there's not really I will, in this class, I would never mark you wrong for producing something that was larger than the smallest possible regular expression. I'm just looking for correctness. And we'll think about it from a couple of different perspectives in case that you attach yourself logically to one or the other. And that's fine. But it's just worth noting both answers are correct. So there are multiple regular expressions that map to a particular language, correct regular expressions. So there's not just one right answer. This is why this class is much harder to grade than a math class. Sometimes it's just you got the right answer, you went through a logical way to get there, great. The issue with this class is there are multiple right answers. A book cannot give you every possible correct answer. So the TA has to go through your logic and validate your logic for your answer that's different from everyone else's answer across the same problem. So it is a nightmare to grade this class. Please do be patient with the grader as he has to go through and figure out the correctness of everyone's logic for every single problem for the size of assignments that I assign. It's not feasible to turn it around instantly all the time. Same with exams. I try to give you a turnaround of about a week though. Unless there's an upcoming exam, in which case I apply a little bit of pressure because you want that back before the exam. So we will define the equivalence of regular expressions. If they denote the same language, then they are equivalent. They may not be computationally equivalent, but they do the same thing. What's nice is the other way, there's exactly one mapping. If you come up with a regular expression, there is one and only one language that it represents. Can't possibly represent two different languages. That's cool. For every regular language, there must be at least one regular expression that can recognize it. You cannot come up with a regular language and not be able to generate a regular expression for it. In the same way that you have to be able to draw a DFA for it, you have to be able to draw an NFA for it. If it is a regular language, then any of these tools you can use to prove that the language is regular. So now for any future problem that says prove that this language is regular, you have an additional tool to use. You could draw a DFA, or you could draw an NFA, or you could write a regular expression to recognize it. Ways that we could do this: construct an NFA accepting the language. For part 2, we can generate an expression generating all labels from all walks from an NFA to the start, from the start state to any final state. And actually, we will go through this process later in this course and show that here's exactly how that works. But not for a while. If you have cycles that can be traversed arbitrarily in any order, this becomes difficult. And we will talk about how to prove that something is not regular by going through something that's kind of similar to that as well. I do note this sometimes in this course. I don't expect that we will have time to come back to some extra content, but there is a little bit more here that is outside of the scope of what I plan to deliver over the course of the quarter. So if these things intrigue you and there is a little bit of time, it is a potential research field for you. It is a potential thing that we can come back to if we have extra time. I'm trying to go a little bit slower this quarter so that there's not a whole week at the end of the quarter where it's like, all right, we did everything. Questions on regular expressions at this stage? At this point, all you need is practice, I think. And hopefully you feel like you have the tools to go do some homework problems related to regular expressions. If you get stuck on those, come see me in office hours. I'd be happy to help give you a nudge in the right direction. One last tool regarding regular languages, and trust me, you want to put this class to be taking as long as we can as we're talking about regular languages, because as soon as we start proving that languages aren't regular, the class gets hard. And it doesn't really let up for the rest of the quarter. This is the fun part of the class. So one last way of representing regular languages is that we can build a grammar for it. But we can't just build any grammar in the same way of the grammars that we've been designing and thinking about on this first homework that you have. There are specifications to that grammar that we need to make in order to ensure that the strings that are generated from it adhere to a regular language, as opposed to a language class that is more generic than regular. So refreshers about grammar terminology. We have terminals. Those are characters that are in the alphabet that we use for the language. We have non-terminals that are variables that can be broken down into more sequences of terminals and non-terminals. So think of it like object construction. They're made up of some primitives and some objects, and that defines a new object. Objects are your non-terminals, and your primitives are your terminals. So I really do like thinking of it in that term because you've all done object-oriented programming, object-oriented construction. The way that you need to think about that is very similar to the way that you can break this down and make it make sense. Objects can be made up of other objects and or primitives. Objects must eventually break down into primitives because we can't program a machine to make operations on objects that aren't defined until compile time. The language defines how do we add integers, how do we add floats, not how do we add squares. We need to further define what that means in terms of those primitives in order to be able to do more complex operations. So a regular grammar has to adhere to one of the following two constraints, not both, but one or the other. It must be either right linear or left linear. Right linear grammars can have productions in a couple of different forms. I use this lowercase x to represent some kind of terminal, but a non-terminal must be some number, one or more terminals, followed by a single non-terminal. Or straight to that list of terminals. So x is a string of terminals of arbitrary length, and b is a single non-terminal, 0 or 1 of them. So we can see now why it is linear. If there are multiple variables, we can create kind of a branch where we need to now look at, all right, we need to go search to identify the construction of the first variable and then the second variable. This doesn't allow for that. Every single production has at most one non-terminal on the right-hand side. And all of the characters are always on the left-hand side of that. So this allows us to, in one pass over the string, map the x to the unread portion of the string. And when we hit this b, there is some production that is going to allow us to now say it's possible to generate that and continue reading from the string in one single pass from left to right. So that is a right linear grammar. Think about it in terms of where is the non-terminal in this. So it's right linear if the non-terminal is on the right, and it's the exact opposite for left linear. Whereas the non-terminal, it's going to be on the left. Oops. So there's still only ever one non-terminal. But note that every single production in your grammar has to adhere to that same right linear or left linear rule. You cannot have a grammar where you have one production that looks like this and one production that looks like this. All productions must have the non-terminal on the right or on the left, not mixed. Give you an example. First of all, left linear, right linear, or neither.
I'd call that left linear.
One vote for left linear. Any disagreement? That is a left linear grammar. Everything follows that form where a non-terminal is defined in terms of a single non-terminal followed by a string of terminals, single non-terminal string of terminals, single non-terminal empty string of terminals, and no non-terminal, that's okay, followed by a string of terminals. So you could imagine generating a string starting from the start non-terminal by following legal sequences from this. And you see that we start from S, we generate this capital A, A, B. We now need to define this capital A in terms of some production. So we'll turn just this A into that sequence, which gives us this. then the A becomes a B with that production. Then we get to just the string because the B goes to just that last A. And you can see how now we're kind of chunking the string from right to left as we create it. So this AB is the very end of the string. Then we generate this AB that is next, and then we generate this A that is at the very beginning. So we're moving from right to left instead of from left to right as we reveal the string. But we're making a pass kind of in chunks from right to left. Because we can go through this derivation process, this shows us that this string, AABAB, is in the language. Left linear, right linear, neither. A vote for neither, why?
The B production is left linear and the A production is right.
Yeah, this is left linear, so the non-terminal is on the left. This is right linear because the non-terminal is on the right. A grammar has to be consistently left linear or consistently right linear. This one is not. So it is not a linear grammar. It's not a regular grammar. So even though it adheres to those individual rules, there's a big or there, exclusive or, not an inclusive or, that this does not adhere to. Does everyone see that? Any questions about why this grammar is not regular? Let's talk about a really fun process. That is, given that we have a regular grammar, how could we construct or think about making a DFA or an NFA out of that grammar? Because if both of these exist for the same class of languages, then it makes sense that we might try to have some kind of translation algorithm that would convert one to the other, if possible. It makes it easier to start thinking about it in terms of right linear. So we will give you a grammar that looks like this. Just turning these into variable notation, variable 0, variable 1, etc. Note there's a loop between variable 0 and itself through variable 1. This is also recursion. So we're going to start with states representing each non-terminal. So we're going to draw, how much more space am I going to need? We're going to draw a state representing V0. And we're going to draw a state representing V1. V0 is our initial state because it is where we start in the first production. How do we transition from V0 to V1? On an A, we read an A and we end up in V1. It's kind of inherent in this production that says on an A, we go from one to the other. How do we get from V1 back to V0? On an AB, we can't read two characters in one edge. So we're going to make a third state that reads on an A. It's not a variable in this, so you need some other notation for this. So maybe we make this Q0. Doesn't really matter what you label it. And then on a B, we get back to B sub 0. From V1, there is something else that we can do. We can read a B. Where do we end up? Which state, V0, V1, do we end up in after we read that B?
Trap state.
It's actually an accepting state. Because when this V1 becomes that B, we've finished generating some string that is in the language. So from V1, we read a B, we end up in what's actually the only accepting state that we'll just call Q1 for the moment. Is this a complete DFA. Note that you can just make it an NFA and just say, all right, we're done. But is it complete? Is it a total function? No, we need to be able to, from V0 read a B. We don't have the ability to do that. It's not defined in this grammar. So there is no such string in this language that reads a B from V0. So we can make our trap state on a B that loops on itself. V1 has outgoing edges for A and B. Q0 does not have an outgoing edge for an A. So we can make it. And there's a complete DFA from this idea. I guess we need to define transitions out of Q1. Once we read that B, is there any definition for what comes after that or before that? So yeah, if we see anything, we go back to the trap. What's a string that's in this language? Looking just at the grammar, how can we generate some string in the language? AB. We go from V0, we read the A at the beginning, going to V1. V1 can produce a B and terminate. It's exactly the same as starting at V0. A, B, we end up in a final state. This helps our intuition that might be correct. Any other string that is in the language?
A, B,
A,
sorry, A,
B, A, B?
Yeah.
Yeah, we have A, B, A, B, and we end up in a final state. What's a string that's not in the language? AA. We read AA, we end up in a non-final state. So I like this construction. I don't immediately see something wrong with it. Probably need to spend a little bit more time if this is a homework problem to be absolutely sure that this construction is complete, correct, and perfect before I would submit it to myself. But that is the general process that you go through to create some kind of state machine out of that. And I find it way easier to think of it in terms of a right linear grammar. It's a little bit more challenging if it is left linear, but it's very possible. Questions on this construction or the process we went through to generate it?
If it were to be left linear, what would you have to translate on? Because you can't
Yeah.
assume the non-terminal.
Yeah.
You have to have land transitions and make an NFA.
Yeah, you would still start with these, but now you would be reading backwards from one to the other. So you would be creating edges in reverse. If I read these things, then I end up in that state from this state. So instead of having the arrows reading when I read A, B, that's an arrow in this direction, you would be reading the exact opposite. The V0 would be here. So it's if I go from V0 to V1 on that AB, so you kind of go backwards and make the reverse. A little bit more painful, a little bit more annoying, but very possible. So here was a solution NFA. I went all the way and turned this into a DFA, but you only need an NFA to show it. So if you were ever asked to do something like convert this grammar into a state machine, it's way easier to just do it as an NFA. How about making grammars from regular languages? We'll end today with one of those examples. So here's an example language in terms of a regular expression. Construct a regular grammar from. level, and that moment of insight happens immediately.
I mean, I was surprised by how simple the process of converting to a DFA from a grammar was.
Yeah.
This like was so the non-terminals become states and then terminals become edges. Like
Mhm.
basically, there's more to
Yeah.
it, but I was like, really? Like, that was,
Yeah.
I was expecting something way more complicated, like what we did with the
DFA minimization.
just the other day. Yeah, yeah, with comparing equivalence classes. I was expecting something like that. We have to like analyze like how you
Yeah.
move through the DFA.
Regular languages are so nice. Man, when things just align into regular languages, it's just, oh, I love the best language. So a general trick to this is going to be to figure out how much of this string can I state for sure before there is a variable associated with it. Where there's a branch where I can produce multiple different strings from this. So we know that every string in this language starts with AA. We don't know necessarily what comes after that, but we could start with a start non-terminal arrow AA, and this isn't necessarily done, but we know that every string starts like this. The natural way for me to think about this is in terms of something that is right linear, because you read as much of the string as you can before we have some kind of branch or variable. Once we have that variable, let's just put it there. We don't know what comes after this. When we want to define what that looks like, we know this is going to produce some number of bees. What is a production that would specify some number of bees? Be able to generate a bee and be back in that same spot to generate more of them. Once we're done generating those bees, what would we want to do?
And
Lambda would say that we're done with the string completely. Since there's something that has to come from there, it's very close. We just need some other non-terminal. Something that says that what comes after that? Something. And then that something could be defined to be just that last A. Now note that we could just take this A and move that right back here and eliminate the need for this, but that's only because it's the last character in the string. And that requires a little bit of meta-analysis of the string that we wouldn't necessarily have when we generated this. So this is the nice general procedure that allows us to say that we have this one-dimensional recursion when we have this kind of one-dimensional repetition in the regular expression. What would happen if this entire thing were started?
I don't think it would be a regular language anymore.
It is. It adheres to those same regular expression rules. Yeah,
You could have the B become A, C, or AS.
it's S, yeah. When we star closure that sends you back to the beginning to read beginning from the very beginning, it's the same as reusing your start non-terminal. This allows for a two-dimensional recursion. Of course, since this is optional, we would need some way to terminate it. When we select this, this would say we are done now looping this process. So I naturally think of and see this as loops and or recursion. Since they're the same thing, and this is a great way to show that they're the same thing. We just now state that we can repeat something an arbitrary number of times. So we allow for it once and put yourself back at the program point that you were before you made that decision. This is a way of doing a two-dimensional loop, where inside of this loop, we have that loop. Every time we go through this process, we can go through this process some number of times. So you can make the exact same kind of grammatical construction if you're going to have a loop inside a loop inside a loop. And it allows you to now have the structure of that, which is all regular in nature. You don't actually need memory, more memory than is defined by this process to be able to do that. That's why something like a loop inside of a loop is in its own separate scope. Because we don't need to reuse that memory once that loop is done. Only things defined outside of that scope need that permanence. Interesting way to think about it. Right, yeah, this is basically the end of this idea as well. For more complicated regular languages, use the transitions of an equivalent DFA or NFA to show that we can produce the grammar. The only thing that I think is more relevant than exactly what's on the slide is that concept of further repetition, since regular expressions really only have those three concepts: repetition, concatenation, union. All of those are embedded in the grammar. Repetition in terms of reusing non-terminals, concatenation in terms of just being able to make a more complicated right-hand side, concatenating terminals and non-terminals, and union with the or. We can take this or that, this right-hand side or that right-hand side from the same definition of a non-terminal. So these ideas all map onto each other in some capacity. So if you're struggling to produce a regular grammar from a language definition, see if you can produce a regular expression and then convert that regular expression into a regular grammar. Or draw a DFA for it and then turn that DFA into a grammar, or that DFA into a regular expression into a grammar. Since they're all related to each other, you can start anywhere and convert. And I think that process will also help you to see why they're all related. And also just to have more tools to be able to solve a problem. All right, I think that's a great place to end for the day. We're right at the end of this slide deck, and we're right at the end of the fun part of the class. So we will come back next week.
Wait,
and
fun part?
we're gonna start talking about really fun things.
Were you gonna
Like,
give us the study guide or is that not?
yeah, I will put it on Canvas
Okay.
as soon as I get to my office and get through any requirements of people up there. But I do have office hours starting now for anyone who would like any other assistance. But yeah, the very next thing we are going to is how to show that a language is not regular. And that process is not fun. So
Let's not do it.
it's very important, and it ties to really important
Trinity.
comes in the course.
Regular languages.
But yeah, it is not fun to think about and come to terms with. So starting next week, let's really advocate for yourselves for
I have seen your.
learning and getting the repetition that you need to be able to solidify this idea. It will not be on the first exam.
Or, yeah, cybersecurity.
Is it like this coming idea? Like we did with one?
Yep. It is a proof type. It in fact is exactly a proof by contradiction, but it's a very similar type of proof by contradiction. And it's something that I can help you see the logic of and how to construct. But yeah, for those of you who hate math, this is where the math kicks in.
I like
This
that.
concept we just covered is on the exam, right?